explain. And as we all just heard, I suppose, this meeting is being recorded. So if any of you are tuning into this in the future, welcome for this second recording as well. What we are going to do is get you even further on the way today toward being able to do meaningful, accurate land cover classifications. And that is where we'll end after several hours from now. Rylan is going to be your main host for the day. You heard from him a little bit yesterday, but you'll hear from him a bunch more today. He has really grown into a person who can use maps extremely well and Earth Engine extremely well in the last maybe 8 or 9 months, I guess, when he started. When he began, he was a computer science student finishing his undergraduate degree who had no experience whatsoever with GIS at all. So you'll hear from him in a couple of minutes. We're also, before he starts, I wanted you to get a chance to hear from 3 other people in my lab to have them talk about the particular aspects of Earth Engine and ecology in general, but Earth Engine in particular, those particular aspects that they're doing within my lab. In case they don't mention it, they are all former beginners in Earth Engine also. They, let's see, Mary, who you'll hear from, and Cash, who you'll hear from, are both pre-undergraduates, I guess is maybe the right way to say that, almost undergraduates. And they'll tell you about their transition from computer science to working with Earth Engine. And then you'll hear from Eliza Deutsch, who's a postdoc in my lab, who has her own really interesting journey and great results that happen all across the continent of North America, and she'll tell you about them. So, Rylan, how about if you could bring up the part 3, Who Are We? And let's go to slide number 8. And Mary, I will remind people by looking at slide 9, then I'll hand it to you and you describe slide 10, and then you should be able to share your screen after that. Okay, so as Rylan hits present, what you can see here is something that you saw yesterday. So everyone looking at this should have, probably should remember this from yesterday. What it is the algorithm that we've developed within my lab for going from images that are shown there on the left with all different types of platforms. You can see them listed, Landsat 5 and Landsat 7, for example. And then we create a rough daily classification from them. And then we work with bulk BULC to create a land cover time series. So that, I think I maybe mentioned kind of in passing, I'm really happy with it and it works great. The downside is it's done through programming. And so there's a real obstacle for just kind of casual users who don't know programming perfectly, or also don't want to look through a 1,000 line program in order to find what to change. And so that is where Mary comes in, and she will describe what she has been doing in my lab starting in January, I think, if I remember right, the end of January. So in just a few months, she has done what you'll see here. So I'll turn it to you, Mary.
Can everyone hear me?
Mm-hmm.
Okay. Hi, everyone. My name is Mary. Basically, I'm creating a user interface for like an existing program. First of all, I just want to say that I know like the bare minimum of what bulk actually does. My job is to take the algorithm and create an app that allows the user to manipulate the data. Basically, the user will input parameters and I take those parameters using the bulk algorithm and I print out the results. Like Jeff said, it makes it easier. As you can see in the image, the user will just have to input what they need instead of going through a 1,000-line script. So the image you see is actually a mock-up of the application. It's how the app is going to look like. And if we click on the link below, you'll be able to have access to my script and the app. So is it okay if I share my screen? Okay, so just, okay, can everyone see my screen? So let's go here. So this is how my script would look like. It's a lot, as you can see, it's like over 1,000 lines. But what the user will be able to see is this. So I gave them an option. They could input the they could input the parameters one by one, or they even have the option for automated if they want to tweak just a couple things. So basically, once they've input every parameter and they click apply parameters, they would have 4 options for output. So they would either have movie. So basically it's like the time lapse of a multi-band image. They would also have the option for mosaic if they want to see the results, an overview of the results. So you could track exactly where the change happens. So this shows every single band. You also have the option for airstrip. What airstrip does is it displays each band so you could have a closer look to where the changes happen, and you could browse through all of them. And the last one would be zoom. Basically, it takes the results of the book, and wherever, let's say you think this part is particularly interesting, it's a zoom version, and you'd be able to capture it and use it for save it as a result. So those are the main 4 things that like how the bulk algorithm results can be displayed. I think that's it. Jeff, you're muted.
Okay, perfect. Yeah, well, thanks, Mary. That's great. And so both Mary, well, I'll tell you what, let's go to the next slide, and then I'll mention you and Cash together sort of in your role within the group. So we will now go back to Ryland for the slides. It goes next to Eliza, I think.
Okay. Yes, hi, I'm Eliza Deutsch. I'm a postdoctoral fellow in Jeff's lab. And I came into the lab having done quite a bit of work in remote sensing and in GIS, but I had never used Google Earth Engine, and found very fast that I had to use Google Earth Engine because my project required me to process massive amounts of imagery. I'm just going to apologize because I have my toddler just home from daycare. And yeah, but my work, my project is part of a large-scale Canadian project where we are trying to get a sense of the health of lakes across the country. And my particular project was to find some way to upscale measurements from a couple hundred lakes to hundreds of thousands of lakes across the country. And to do that without Google Earth Engine would have taken at least the 2 years of my postdoc, if not more, just to process the imagery. Sorry, George. What we did is we looked at the relationship between Secchi depth, or water clarity, and satellite reflectance data. And then we developed an algorithm in order to relate the reflectance information to the field data. And from there, we applied the algorithm to 100,000 lakes, 150,000 lakes, 4 years of data for each lake, 4 years of summer data for each lake. So, I mean, we're talking about millions of images that was able to be processed in Google Earth Engine in a matter of 2 weeks, as opposed to years as it would have taken before. Could we advance the slide? So the results of my work have been published. The results of the algorithm have been published. So we've developed, on the left, you see the relationship between the, on the y-axis, it says natural logarithm of Secchi depth, which is the field data. And on the x-axis, it says the natural logarithm of the blue over red reflectance information from Landsat 8. And we had a fairly good fit, regression fit. So we were able to then apply this algorithm to the massive amounts of lakes that we looked at across the country to look at water clarity classes for the first time in most lakes in Canada. And we were able to get some very interesting information about where clear lakes were and where very turbid lakes were. And then we were able to relate it to a lot of other GIS variables. But again, this project was, at the massive scale, would have been impossible without using Google Earth Engine. Is there anything else that you wanted me to mention, Jeff?
No, I think that's great. It gives a sense of the scale that's possible. And maybe for a little context, several years before Eliza ever came, before I myself had heard of Earth Engine, we tried to do a project like this for a whole summer. I hired an undergrad to do it. We downloaded a bunch of images, and basically that's all we were able to do over the scope of the summer. We were never really able to complete it until now, when Earth Engine now exists, and so we are able to make great advances, I think, so far within this aquatic world, which is a lot less studied. So, okay, great. Thanks, Eliza. That's good. And let's pass to Cash.
Hi, I'm Cash. But yeah, it's the slide before this one. Yeah. So hi, I'm Cash. I've joined the JeffCardille lab in January. When I joined, I didn't have any GIS experience, but my field is computer science, so I have like a lot of experience with programming. The most recent project that I've been working on since last month is actually exporting a lot of images that cover lakes, multiple lakes across, I believe, Canada, to try to export it out of Earth Engine and store it into a database. The reason why this is important is because when you use data, when you access data on the Earth Engine servers, it's inconsistent, and sometimes it could take a lot of time. And when you have a copy of them offline or like in a database, it's faster to access the data. So there's over like 1,400,000 lakes, and the two data sets that we're trying to export the data for is Landsat 8 and Sentinel-2. And the method that I'm using is actually concentric buffers. As you can see here, it's a lake, and the point in the middle is like the center of the lake. And there's like multiple buffers around it. And in the next slide, yeah, can you? Yeah. So the approach that I'm taking is to traverse through like the centers of the lake, and for each one create the buffers. And once I have the coordinates of the buffers, I filter out all the images in the data set that do not intersect with the buffer zones. And then for those that remain, I take the average of all the pixels in each image for each buffer, and I format it into a CSV file, as you can see on the right. Each row has the image ID, the lake ID that's associated with the image, the buffer size, and then the 3 columns on the right. There's more columns, but I just cropped this so you can see the 3 columns on the right represent the band values for each image. And then the final step is to, once the file is exported out of Earth Engine, I can manually upload it to a database server. And I'm using Google Cloud SQL for it. Yeah, that's it. Thanks.
Okay, great. Thanks very much. So let me reflect a little bit on what it is that they are doing and kind of what what I think they represent for you as new users of Earth Engine. So, not every person who has a job protecting natural resources is going to literally do the programming, right? It's good, I think, for everyone to see the programming and to be exposed, but we might often want to do things that are beyond our abilities. In my case, it's user interfaces. I have no idea how to do what Mary is doing. And so she is able to figure that out. And even though she's tried to explain it to me several times, I still don't get it. But that's the great thing about programming, is that someone else can do that part. I can do the part that I know how to do, work with other people in the lab to do things that I know how to do, pass it to Mary, and she can put an interface on it, and then we can share it with other people. What we're also able to do through Cash's work, I also don't know how to do. He's tried to explain to me several times, like the cloud storage or cloud platform. I can't really keep them straight. But what he represents for me is, this is a person who is, in a slot where you can hire an undergrad to figure things out that you don't necessarily know how to do or have the time to do. And so Cash is going to download, we think, maybe billions of rows by the time this is all done. Yeah. And so it's pretty crazy, given that, 10 years ago, it took a whole summer just to download the information from 10 images. He's now going to have the information from every single image for every single lake, at least in Canada. That also brings up the fact that even for this problem, it's maybe outside the scope of what Earth Engine can do easily. And so through the developers list and through being able to ask people at Google, can you please help us through this developers list, we have a pretty good shot at doing this impossible project. And so even if we get stuck trying to do it with the code that we have, we and you also in the audience can also make requests sort of through Silva Carbon, probably is the easiest path to doing things that are even more complicated than what Earth Engine can easily do. And so for, just to finish, turning to Eliza, somebody like Eliza can come in with a ton of aquatic remote sensing experience, but with very little Earth Engine experience, I guess no Earth Engine experience, a little bit of R programming experience, actually maybe more than a little bit of R programming experience now that I remember the R scripts that you have. But she can pick up Earth Engine first with by leveraging code that we already have in the group, and then getting help from a person who we have in our group, and then now running on her own to do this project that you see here, and the project that then follows on that she's writing up right now. And so this ability to build on work that already exists, we're going to come to at the very end of the session when we talk about resources for how to do more with Earth Engine than what you see today. Also, you have a great connection to Google through Noel and through Sylvia. So that is extremely powerful and rare in this world. And also there is this capability that computer programming savvy students, that people who are already comfortable with programming as a technology, that they can come in and sort of add to your GIS experience in order to solve the problems that you want an answer for. So this ability to have people either as an intern or as like a summer job, which is what we're doing now. They began as interns. That's something that I really want to recommend, so that if you finish today and you think, that's great, but when am I ever going to do it? My advice would be, it's really fun to do it, so try to figure out how to do it. But also, if you get stuck, hire somebody who can do it, or make some connection with the university where they are basically producing students who know how to do things like this, like what we see now, at a very large scale. And so I think that's where we'll leave that part, the review of what it is we do in our lab, and the reasons that I think that they are doing good work by leveraging the knowledge that they bring in, and also leveraging what it is that we're able to do in Earth Engine and what we've done pretty recently. So Mary and Cash and Eliza, you're welcome to stay, but of course you guys know all this stuff already, so you can go ahead and tune out and go eat dinner and take care of your young one, and we will catch you in a day or two.
Hi, everyone.
Thank you for
Bye,
having.
everyone. Have a good
Yeah,
evening.
thanks very much. Thanks for coming. All right, great. So now we will turn it to Rylan.
Okay. So we'll be doing part 16 today. So there's the link to the document if you need to find it again, and a link to the Earth Engine code platform. So hopefully yesterday or the day before you made it through to step 15. And then today I'm going to walk you all through section 16, rapid land cover classification. And then at the end, we'll split you into groups and send you off on your own to kind of build upon what it is that I'm going to show you. So I think you can see both my Earth Engine on the right and the document on the left. It's a pretty small group today, so if you think I'm going too fast or too slow, please write in the chat and I will adjust accordingly. But basically we're going to be copying the code from the document and pasting it into the code editor, and I will kind of explain what it is that we're doing. So we'll start here. So the first thing we're going to do is we're going to work for an entire country. To get the borders of a country, we're going to use an Earth Engine dataset that already exists, which is this USDOS simple country boundaries, and then we're going to go get a country of interest. And so I'll be going to use the Solomon Islands, which is called Solomon space IS, not fully spelled out, Solomon Islands. And then we'll add this to the map. So basically it just goes into this feature collection that already exists in Google Earth Engine, and we're pulling out the boundaries of the country of interest, and you should feel free to use whatever country you're in or anywhere where you currently study. And so how did I know that this was what I needed to write? So first of all, we're applying a filter, which is going to go through every feature in the collection and basically give us a true or false test. Does the current feature in the collection match this? And so we're applying an equality filter. So it's going to say, does this property of the feature equal this? And so what is country NA? Well, if we search here, this is basically what we just imported, and we can get the full description of everything here. And so we know that country NA is the string of the United States recognized country name. So that's how we figured that out. So basically, we're importing this thing, but rather than importing it through here, we're just directly importing it in the code. And then if you have questions about it, you can go and open that in there. So moving on, the next thing we're going to do is we're going to only be working for a single year. So we've selected 2019 as the year, and we're going to create two strings of year, month, day. So 2019, January 1st to 2019, December 31st. We're then going to use Landsat 8 images to create our classification. And so again, like we did with the feature collection, Yesterday, we imported this data set by searching for it up here, but because we know what the name of the data set in Earth Engine is, we're just going to import it this way. And then the next thing we're going to do is ensure that we remove clouds from the image. So we have this function here, which if you remember from yesterday, we created functions. This is a little bit more complex, and actually I can't fully describe off the top of my head what is happening in here, because this is code that I didn't write. And so a great part about Earth Engine is that there's a community of people writing code, and so you can often find solutions to your problems already. And so where this came from is from the examples. So in Earth Engine, if you go to the scripts and you go to the example scripts, there's a whole bunch of scripts that people at Google have written. And so this is from cloud masking. This is the Landsat 8 surface reflectance cloud masking script that we've just copied here. And so if in your work you use Sentinel-2 and you want to figure out, well, how do I create the cloud mask for Sentinel-2 data? Because we're using things that are specific to Landsat 8, you can go into examples under scripts and open up the Sentinel-2 and figure out how to do that. And so kind of whatever you're doing, if you're interested in user interface things like Mary showed earlier today, you can go and find a whole bunch of examples of how to do different things in this examples set of scripts. So I think that's a really helpful thing to go and look at. And so now back to this. What we want to create in order to do our land cover classification is a single image of the entire country of region based on the year that we're looking in. And so the first thing we're going to do is we're going to take L8, which is the image collection that we imported. We're going to apply filter bounds based on the country, which is the outline of the country that we found. And if you want to know what does filter bounds do, I'm not sure if we showed you the documentation tab yesterday, but anytime you see something in code and you want to know what does it do, we can go and look it up. And so we can see, well, there's two things called filter bounds, but we know that Landsat 8 is an image collection. So if we click on this, it brings up kind of the description of what this function does. So this is a shortcut to filter a collection by intersection with geometry. Items in the collection with a footprint that fails to intersect the given geometry will be excluded. So basically we have L8, which is every Landsat 8 image. And then after we apply filter bounds, we have every Landsat 8 image that overlaps with our country of interest. The next thing we're going to do is apply filter date. Same thing. If you don't know what it does, or you want to know what the parameters you're supposed to give it are, you can look for it. Here it is again. This one's pretty self-explanatory. It's going to get all the images that were taken between start date and end date, which is every image in 2019. So we start with every Landsat 8 image. We remove all of them that don't overlap our area of interest, and then we remove all of them that are outside of our time period of interest. And then the next thing we're going to do is filter metadata. So we can again, look up what that does, which is basically it's going to, every image in the image collection has properties that are associated with it. And we're going to go and find this cloud cover property and say every image with cloud cover less than 50 will be kept, and every image with cloud cover greater than or equal to 50 will be removed. And so how did we know that this was called cloud cover in all caps? Well, if we look up Landsat 8 and we go and look at the image properties, we can see that there's a whole list of all these properties, and every Landsat 8 image is going to have all of this information associated with it. But we can go and find cloud cover, percentage of cloud cover. My screen is a little bit small, but percentage of cloud cover, and then there's some more information. And so maybe you're interested in just the cloud cover over land, and so you could use this property instead. Then we're going to mask Landsat 8 surface reflectance clouds. And so map is a really helpful function, which basically is going to say, give me some function, and then I will apply it to every single image in the collection. And so the function that we're giving it is the one that we wrote earlier, masking out the clouds. And so the first thing we do is we remove any image that has so many clouds in it that it's not useful. And then next, we're going to mask out every pixel in the remaining image that is cloudy, in the remaining images that is cloudy. Finally, we're going to take the median, which again, if you have questions about it, you can look it up in the documentation. But essentially, it's going to say, well, for every image that we have now that's overlapping in this stack, for every pixel, we're going to take the median value in each band of that pixel across all the images that remain that overlap. And then we're going to clip the image so that we only get, we're going to clip it to the country. So any parts of the images that don't overlap exactly with the country, because, for example, there could be a Landsat image that exists over here, and so only partially overlaps with the Solomon Islands, we'll remove what remains of that. And so then to see what this looks like, we'll add it to the map. And if you have questions while I'm going, put them in the chat or raise your hand. Jeff or I will answer them. So, all right. Country name is not defined. Yep, didn't do a very good job. Copying and pasting code.
So Rylan, I'm wondering, do you know what the get info does in that line that you just pasted in?
I do. So this is
it's a
maybe
real little detail, but anyway, go do your thing.
Well, I can answer the question. It's just maybe more information than you want to get on their second day of looking at Google Earth Engine.
Okay, skip it. I'll ask you another time. No problem.
Sure. So anyways, now we have added another layer, which is the image that we just created. So we went and we got every Landsat 8 image. We then removed the ones that aren't of interest to us because we're just looking at the Solomon Islands for the year of 2019. We then removed all the really cloudy images and then removed the remaining clouds from the images and then took the median and clipped it to the outline. And so we can zoom in and see what this looks like. And then we're displaying this as a false color image. So if we created this dictionary that we are passing to map.add layer, which determines how we display the image. And so the bands we're displaying are 7, 5, and 4. And if we want to know, well, what is in band 7, 5, and 4, we can again go and search for Landsat 8 and look at the bands and say, okay, well, band 7 is shortwave infrared, band 5 is near infrared, and band 4 is red. So this is what the Solomon Islands looks like when you visualize those as red, green, and blue. Next, we're going to visualize it in, I think, true color. So this time we're passing in a slightly different visualization parameter, and this time we're using bands 4, 3, and 2. And so again, we can go and say, well, what's in band 4, 3, and 2? And it is red, green, and blue. And so when you pass in these list of bands, you can either give it a single band, at which point it will display the values in that band as grayscale, or you can give it 3 bands, and then it will assign the first band as red values, the second band as green values, and the third band as blue values. So now we'll zoom in again. And let it load. we go. So we have kind of two different ways of looking at what the land looks like, which is going to be helpful for the next step as we create our training data. So I'll just let this load in zoomed in area. So there we go. Looks like we have maybe an airport, some cities, rivers, forests, hills, and we can look at it in two different versions based on the Landsat image. And so the next thing we're going to do, we want to convert this into a land cover classification, and we're going to do this with three different classes: forest, non-forest, and water. And so to create our training data, we're going to start by drawing some geometries on the map overlapping our different regions. And so using the two different layers that we just drew, I'm going to go to the geometry. I'm going to select polygon, and then I'm going to click on this gear here. It defaults to calling everything geometry, which isn't super helpful. So I'm going to call this forest. And then we actually, this is pretty critical. We don't want to import it as a geometry. We want to import it as a feature collection. And then we want to give it a property. And the property we're going to give it is called label. And we're going to assign it the value of 1 and then press OK. And so this looks like forest to me. And so I will draw a polygon around there, and we can go somewhere else, say, still looks like forest to me, but I could be wrong because I've never been to the Solomon Islands. But I'm pretty sure this is a forest. So I'm going to draw another polygon here. Then the next thing we're going to do is, and you can draw kind of a lot of these, but eventually you'll run out of memory when we get to the step where we're actually doing the classification. And so for now, because my goal is to just kind of show you how this works, I'm just going to leave it with the 2 polygons. And so the next thing we're going to do is create our non-forest class. So we'll go up to the geometry, and where it says new layer, we're going to click on new layer. And then we're going to do the same steps. So again, it calls it geometry. I'm going to call it non-forest. Turn it into a feature collection. Add a property. And again, we're going to call the property label, but we're going to give it a different value so that later on we can distinguish between what is forest and what is non-forest. In the document, it calls the non-forest non-forest. You have to remove the dash, so I'm calling it non-F forest because if there's a dash, we'll get a syntax error later on. So this looks like non-forest to me. So we'll zoom in here and the same thing. We'll create another polygon. And this looks like agriculture. Hopefully it's not a forest. So I'll add another polygon. And then because I'm just doing this quickly to give you a feel, I'll stop there. And so then again, we're going to move on to water. So following the same steps again, change the name to water, import it as a feature collection, give it a property called label, and give it the value of 3. So now we have these 3 feature collections. They all have labels associated with them, but the value of label is different for each of them so that we can use label to distinguish between what's on the ground underneath them. And so not a lot of water in the Solomon Islands. This looks like a lake. Wow, I hope there is actually a lake there. Okay, there's definitely a lake there, cool. And then maybe this will show up. Yeah. All right. So I drew 2 polygons for each. The number of polygons that you draw for each doesn't really matter because what we're going to be using is the pixels underneath those polygons. So ideally the area that each of your polygons covers will be approximately the same, but that's not a huge deal for now because we're doing this so quickly. The land cover classification that we make isn't going to be great, but I think the idea is just to give you an idea of what this looks like. So when you create these different layers as geometry imports, they appear at the top of your script, same as if you imported Landsat through the search bar. As you can see, they're each feature collections, and you can open them up and look inside them, and you can see that each of them has this label property that we've given them. So I called mine forest, non-forest, and water uncapitalized, so we'll have to change the script to be like that. And you can see because they're imports, they turn purple when you've spelt them correctly. So make sure you get that. All right, so the next thing we're going to be creating our land cover classification using a CART model, which is a classification and regression tree. And a classification, a decision, it's basically a decision tree that either does classification or regression. We're going to use it to do classification. And a decision tree is essentially a bunch of nested if-else statements based on the values in the bands. So it'll be something like, if the value in band 2 is greater than X, then check if the value of band 3 is less than 4. And if both those things are true, then we'll assign it one classification. But rather than us hard coding in these if-else statements, it's going to learn them based on the training data that we just created. So basically what we're doing here with these merge statements is combining the 3 feature collections that we made into one feature collection called training, where each feature is going to be the polygon that we drew plus the label property that we added to it. Okay. Yeah, that's an excellent question, Chris. And I agree with Jeff. There's no easy rule. And it just kind of, every time you do it for a different problem, you'll come up with like a different answer for how many you need.
Yeah,
so,
I think, could I jump in on one little thing?
For sure.
I think for me, I when we're doing this roughly like this, I do the same thing with creating polygons like that, maybe a triangle or a rectangle. The risk of that is that without seeing it, we enclose like a very small river or a creek. And if we're trying to do forest, right? And it looks like it's only forest land, but up real closely, part of maybe one little part of that polygon is water. What that would then do is teach the classification algorithm, listen, forest is green, but it sometimes looks just like water. If you see that, you should call it forest. So having very pure classes is one strategy, but then it becomes also hard in like in a town that has trees. Well, a town that has trees looks pretty close to a forest. And so they can really be, it's the hardest thing, I think, in remote sensing, not getting the algorithm to run, but to do it and get the answer that you hope for at the end. And yes, we can use points. That's part of where I'm going, and part of what I was happy to hear with, I think with Collect Earth, you have a lot of points actually that you've gathered through Silvocarbon, if I understand this right. And if so, that gives you more likelihood that any particular point is good and that you have clean classes. But instead of having 1,000 pixels that he just enclosed, you have maybe 30 pixels or 50 pixels. So there's a little less power to have the algorithm discriminate, but sometimes it can do better with pure classes like this. So Rylan, you can feel totally free to disagree with that as well too. So I'll turn it back to you.
No, I definitely agree. And if I were, not just trying to quickly give everyone a feel for how to do this in Earth Engine, I would never have drawn this polygon here and been satisfied that that is all non-forest, because definitely, well, it looks like a city. There's definitely trees in there, so this polygon is not ideal. And so definitely using points is probably better, and especially if you have points that have been like verified on the ground, that would be even better, because then you know for sure that the point is actually representing what you think it is. But for now, just because I'm doing this quickly, I am going to be satisfied with this polygon. Okay. So the next thing we're going to do is use, okay, so the first thing, we're not using every single Landsat 8 band. So we're only using bands 2 through 7. So again, we can see what is in those bands by searching for Landsat and looking at it. So we're not using the coastal aerosol band, we're not using the cirrus band, and we're not using the quality assurance bands. But everything else is being used. And so the first thing we do is we take the nice composite image that we created earlier, and then we're going to select only these bands, and then we're going to sample regions. So we pass it in this collection that we created, which is all of the polygons that we drew. And then we're asking it, basically what sample regions does is it says, give me some geometry, and I will extract each pixel from this image that we input, and the band values from all those pixels, plus any number of properties in the geometry that we assigned. So the label is what we created earlier, the 1, 2, or 3. And then we're giving it the scale so that it knows how big a pixel is. So this samples now is a feature collection where each feature is the value of all the pixels that overlap with one of these polygons, and then plus a value that is the label that we assigned to the polygon. And so this is what we're actually going to use to train our model. So the model that we're using is called SmileCart. And if we're interested, we can look in the docs. It's a classifier. And so these are all of the classifiers that are just built into Earth Engine that you can use. And so the one we're using is called SmileCart. And you can, if you're interested, I guess, go read the paper. But we're not going to get into too much details there. It has a few parameters, so you can play around with the maximum number of leaf nodes in each tree, and you can play around with the minimum leaf population to try and improve the results you get. But for now, I'm just going to leave those blank, so it will give them the default values. And then we're going to train it. So if you want to know, well, how do I train it? Again, we're going to go here. It's a classifier. It has this train function associated with it. So we give it the features, the name of the class properties, and then the input properties. And then there's a few other things, but we'll ignore those for now. So the first thing we do is we create a new classifier, and then we train it by giving it the samples, which is all the pixels that overlap our polygons. We tell it of the properties associated with each feature in samples, which are the things that we're going to use to predict, which is bands to use, and which are the things that we're trying to predict, which is the land cover label. And then we can look at what it looks like and run this code and see what we get. So here we go. We can see that the class property is label, which is good because that's what we gave to each of our things here. And input properties are bands 2, 3, 7. So it looks like everything is working properly up to this point. And then the next thing we're going to do is actually, we've now trained it, because once you call train, the model is trained, and then we're going to actually make our classification. So again, we take the nice image of the Solomon Islands that we created earlier. We select only the bands we're interested in, and then we call classify, which we can go and look at. So again, this is a method being called on an image. So if we go to image, and we look at all of the methods you can call, or functions you can call on an image, classify, basically just give it any classifier, which again, cart is just one of the many that are available in Earth Engine. And then it will apply this classification and regression tree to each pixel in the image, creating a new image where each pixel now holds the classification. And then we can add this to the map. And it will take a moment to run, so let's zoom in.
Hey, Rylan, as that's running, can you just remind me what was the time frame of imagery that you used to make that composite?
A single year, so it's all the
year,
images in 2019.
Okay, and it's pretty clear, huh? That's great.
Yes, because we filtered clouds twice, so there are a few places where there's no image, like you can see here as it loads. This is like a place where in 2019 there was never cloud free. You can see through to the map underneath in those areas.
Okay, right. Okay.
So this is the classification we created. I'm going to change these names. So in the palette here, we're giving it these hexadecimal codes for the colors, which is, if you are familiar with how that works, you can use that, but you can also give it, you can just spell out colors in English, and there should be about 9 or 10 like pink, purple, blue, green, which probably doesn't have things like chartreuse, but most colors that you want, and it will interpret those as colors. So I'm just going to change that so that it's easier for me to tell which color is which. So this is what it created. This is our classification. I don't know, it doesn't look great. I think probably it looks like it's labeling these rivers as non-forest instead of water. But I think for a first try, and for spending less than half an hour on it, it's not horrible. So that's kind of the end of the demonstration. The next part, we're gonna create some breakout rooms and put you into them, or I think let you self-assign yourself to breakout rooms to work in groups to kind of take the script that I've just walked you through, run it for your country of interest. If you are feeling confident or interested, improve it, add additional classes, play around with maybe different classifiers, or play around with the hyperparameters to the classifier that I didn't touch. And then we're going to ask you to put together a single slide. So I'll go show you, hopefully. While this loads, yeah, so Trina, we did 2 different ways of masking clouds. So the first thing we did is we said any image where the cloud cover across the entire image is greater than 50%, so more than 50% of the pixels are cloudy, we just remove that image from our computation because we say it's probably not worth our while to include it. And then we applied this cloud mask to each remaining image. So this is this function here. And basically what this does is it uses the QA band, or the quality assurance band, that Landsat creates to determine which pixels in the image have clouds. And then it masks them out so that we don't include them when we take the median value. So the first cloud filtering is to just remove any images that are too cloudy to be useful. And then for the remaining images, we keep them in, but we mask out their cloudy pixels. And so when we take this median of all the images, if 10 of the images for a pixel were cloudy, we don't include them in the median. So we are including only the non-cloudy images and only the non-cloudy pixels when we take this median, so that the median isn't completely thrown off when you have a bunch of really bright cloudy images. Yeah. So we just ran through this. So this is what we're going to ask you to do. We're going to split you into groups to go and do kind of a land cover classification. And this is from a previous time we ran this tutorial, and you can go in and fill out, give us like an image and talk about what you did and what worked well and didn't work well. And so I'm not sure exactly how long we're going to give you, but at the end we'll come back together and give you each of the groups like 5-10 minutes to talk about what happened. So I'll pass back to Jeff at this point, I think.
Okay, sure, that sounds great. Why don't we move those blank posters up like to the top, let's say? Unless you think that's more confusing than it needs to be. But okay, so what I will do is I will go to the breakout room tool, and I'm going to create too many breakout rooms. I will create 7 or 8 breakout rooms, and I will let you each choose the room that you go to. So what I would suggest is if you know 1 or 2 people who you would like to work with for something like an hour, I think is approximately the idea of what we're looking for here. If you know 1 or 2 people, you can just type in the chat if you want to as a way to organize, and then go pick a room, pick any number. If there's already someone accidentally in that room, you have other ones you can go to. And then if anyone is left, we will pair you up and send you into a room. Okay, so you just pick any room number you want and meet up with whoever you want. So I'm going to click now, what that should do in this moment would be for you to see now at the bottom where it says Breakout Rooms, the bottom of the screen, you should see that, and then you can jump into rooms at when you want, how you want. And this is the first time we've done this way. So if it's confusing, just let me know. We're not sure if this will work, but we're hoping it will.
Jeff, what were you thinking in terms of, do you have an ideal number of people per room?
Yeah, I think 2 or maybe 3. I think if it's 1, ideally no. 5 is just that not everybody would be able to do something. So I'm saying 2 or 3. But if you, that's a good way to do it. I think if you have 4, maybe consider splitting into 2.
And they're going to work on a classification of a country of their choice?
That's right. And
Okay.
so ideally, if you have a place that you can agree on of a location, then that's a good way to assemble into a group. So we'll just give you a minute to go, and then anybody who's left, we can talk.
I also think